All right, we're going to work through problem 5.1 from Taylor's Classical Mechanics. This is a problem using Hooke's law from chapter 5. So this problem states that we have a massless spring that is an unstretched length of L naught and a force constant of K. One end is attached to the ceiling, and we're going to hang a mass M from that. We're going to have a mass M. I'm actually going to redraw our spring a little bit, show that it gets stretched out here. We have a mass M we're going to hang from our spring. And now we have a new equilibrium length. This new length is L1. So we went from L naught down to L1. Now we want to write down the condition that determines L1. And suppose now that the string is stretched a further distance. So we know that our force of the spring is negative kx, showing that the force opposes motion. So if we take that to be upwards, we're going to just say our force is kx going up in the positive direction, and we're taking downwards to be our negative. So we know from this statement that our change here, this is our x, and x equals this bigger length minus the smaller length, L1 minus L naught. So we know that. Now we know that our force of gravity is acting here, and this is mg. Because we're making that our negative downwards, we're going to put a negative in front. So from this, we know that our net force must be 0 because it is at an equilibrium. So F net equals 0 equals our kx. So our k times L1 minus L naught minus mg. That is equal to 0. In other words, the force of the spring, the restoring force of the spring, equals the force of gravity, which we're saying that K L1 minus L naught is equal to mg. The same thing that we set up here. So using that, we're going to add a distance x beyond the new equilibrium length. So we'll call this the new equilibrium. Now we're going to add a distance x. So our formula is going to look something like this: x plus L1 minus L naught equal to mg. In other words, and we want to show that our net force, the spring plus the gravity, on the mass is negative kx. So what we can do is our net force equals k times x plus L1 minus L naught. We can call our gravity, there we go. And because we're using positive, we can make this into a positive kx. Instead of showing that it's a negative kx, we can use a positive kx. We can also go about it like this. We can change this around, show that negative for our restoring force of the spring minus L naught plus mg is equal to negative kx. It's the same formula. You notice you just multiply through by negative 1 on both sides. Same formula. So now we're going to work this out. I'm going to show our negative kx minus k times L1 plus k L naught plus mg equals negative kx. And for this statement to be true, these are going to go away. And we're going to be left with k L naught minus L1 plus mg equals 0, which is the same as saying that our mg equals k L1 minus L naught, which shows that our force of gravity is equal to the force of the spring. So we've gone ahead and shown that. For this statement to be true, the force of gravity must be canceled out by the force of the spring to lie in an equilibrium position. So we want to prove the same result by showing that the net potential energy, the spring potential energy plus gravity's potential energy, has the form of u of x, it's a function of x, with a constant plus 1/2 kx squared. So we want our u of x, this is for part B, to be a constant plus 1/2 kx squared. In this case, our x is, we're going to say that that is x plus L1 minus L0, that distance that we've gone ahead and shown. And we know that our spring potential is 1/2 kx squared. Our gravity potential is mgx. We can tack on a negative onto there because we're talking our gravitational potential energy is going downwards. Spring is restoring upwards. So our total potential energy is the spring plus that gravitational potential, and that's going to be 1/2 kx squared minus mgx to represent that downward potential energy. And we want to prove that this is equal to 1/2 kx squared plus a constant. So we can go ahead and plug this in. K x plus L1 minus L0 squared minus mg x equals 1/2 kx squared plus a constant. So working this out, we're going to have 1/2 k. Make that look a little bit nicer. I'm going to do this in brackets. We're going to have the first, just so I can see it a little easier here. And end up with x squared plus xl1 minus xl0 plus xl1 plus L1 squared minus L0 L1 minus L0 x minus L0 L1 plus L0 squared. Okay, so grouping things here, we're going to end up with a 1/2 kx squared when we distribute that out. And then we can group some things together. These two, 1/2 is going to go away, times that 2x L1. 1/2 is going to go away. We're just going to end up with kx L1. Do the same thing here. Minus kx L0. Similar thing happening here. Plus 1/2 k times, I'll write them separately for now, L1 squared plus 1/2 k L0 squared this is going to be a 2, that 2 is going to go away. We're going to have plus or minus kx L0 L1, and then we got to remember that minus mgx at the end. So we're seeing here that we have some terms here we can pull out a kx from. So let's leave that 1/2 kx squared in, plus kx times L1 minus L0. That takes care of these two. Now from these, if you don't recognize this, this is a perfect square. So we can pull out a 1/2 k. This is going to be L1 minus L0, quantity squared, minus mgx. And we want to show that our 1/2 kx squared plus kx L1 minus L0 plus 1/2 k L1 minus L0 squared minus mgx equals 1/2 kx squared plus a constant. So we can get rid of those guys. Now, we know that Kx, L1 minus L0 plus 1/2 K L1 minus L0 squared minus mgx must be a constant. And this concludes our problem. We've gone ahead and shown that that works out to be a constant. Using the net potential energy up here, we use the net force to show those cancel out and that our net force is indeed equal to negative kx. Could have gone about it using kx as well, just using the opposite of signage, of course. But that covers entirely what the problem was asking for.